My name is Donald Telian, and I'm excited to share with you today the two things that make serial links work. Really, just two things. We haven't met previously. I've been doing signal integrity for 40 years on hundreds of different products, designs around the world. At the moment, I'm currently transitioning my career from design work to now writing and teaching about the things I've learned. So before we begin, if you're not familiar with my book, if you want more information on the different slides, you can go to this page and section in my book. I also want to invite you to my live 2-day class. You can go to my website, sciguys.com/training for more information on that. And if those aren't working for you, throughout this presentation, there's live little bubbles you can click on to find the information I'm talking about online. My goal is to make sure you succeed with your designs. So here we go. Kind of a simple agenda. We're going to start by discussing why serial links work. To really understand why they fail, I'm going to give you a very quick introduction on why they work. Then we'll get into the leading causes of failure. And then most of our time will be spent on number 3 here, how you're going to make your links work and avoid those failures. And we'll conclude with a welcome to Gen 2 SI. That's what is happening here today. And that's what I write about, and that's what I teach. So why does serial links work? There's really 2 reasons. So let's take a look quick at a serial link. There's really just 3 things you have to think about. You have the transmitter, the receiver on the other end of the link, and whatever it is that connects them in between. You will hear me refer to that as the channel, perhaps. The transmitter's job is to inject around a 1-volt signal into the interconnect, but unfortunately, these days, the interconnect is pushing up to about 40 dB loss, so that means you only get 1% of your signal at the other end, which is 10 millivolts. So somehow, the receiver has to transform that 10 millivolts into something that the IC can understand and act upon and recover good logic levels that were originally sent by the transmitter. So, number 1 reason why they work is because we can transmit that 1-volt signal through the passive interconnect with 10 millivolt accuracy. This is the mainstream practice of signal integrity. There's obviously lots of things to know and do about the passive interconnect to make that happen. That's just one of the reasons. The other reason is related to the fact that if we look at the signal at that receiver, we really don't have any I. We don't have a valid logic level. So the number 2 reason why things work is this black box here that's within your receiver called EQ or equalization. So that lives to take that tiny little 10 millivolt signal and transform it into logic levels. And once that's done, then now we actually have a signal, or we might say we have signal integrity because our signal is back now. So those are the 2 reasons why serial links work. So now we can talk about why they fail. Now, not surprisingly, the two reasons why the links work are also the two reasons why they fail. If those two things are not done correctly, then we have failure. So now I'm going to flip the order because the number one problem is not getting that equalization configured correctly. So if you remember a couple slides back, we need to recover a valid signal for the internal logic on the other end of the serial link. And that is the job of the equalization. Obviously, if that's not configured correctly, then my serial link fails. Number two is if I don't manage that passive interconnect correctly, then I fail to preserve that 10 millivolt accuracy that I'm counting on to get my link to work correctly. So in practice, and as you read in the invitation to this webinar, there's three reasons, and here they are. Number one, and this is what I see in practice, the number one reason serial links don't work is the equalization is not configured correctly. Number two and number three relate to maintaining that 10 millivolt accuracy. If you think about it for a minute, little reflections in your interconnect or a little bit of crosstalk, it doesn't take much to cause a 10 millivolt failure. So there's some basic things we need to do and understand to get our interconnect implemented correctly. So now that we understand what makes it work and what makes it fail, now let's take the deep dive. What am I going to do about this? How am I going to make my links work? So obviously, with the three problems being EQ, discontinuities, and crosstalk, well, now we're going to step through those three problems. Instead of looking at them as problems, we're going to look at how you solve those problems, how you design correctly so they're not problems and your link doesn't fail. So here we go. Number one, we've got to configure the EQ correctly. Now, many try to wash their hands of this because the hope is, well, my ICs just go off and figure it out. They communicate with each other. They do back channel or negotiation, auto negotiation, training, all this complex stuff, and somehow they just come to a great answer. But in practice, I don't want to be the bringer of bad news, but in practice, that really doesn't work well. So I spend a lot of time with my customers kind of retreading that, trying to recover that, helping them perhaps override the default equalization so that their system works better. I've published quite a few materials on this, papers that show 200% margin improvement. Please refer to the published works on my website for more of that information. But for the purposes of today, what can be done? Well, I'm going to give you two simple steps. Number one, go get access to your transmitter's EQ software registers. Now, you may be thinking, wait, I'm doing signal integrity work. You know, why are you talking to me about software? Well, here we are. This is what's making your signal, your system work, and also what's making it fail. So step one, you can do it. Go find those software registers. Step two, turn off your transmitter's equalization. Now that sounds like a very strange fix, but oddly enough, that has solved many signal integrity problems, even including crosstalk. So I posted in mid-April on LinkedIn about turning off your transmit equalization, and right away somebody came in with these images and said, hey, guess what? I just did it. And he showed the before and after. Those are the two waveforms there. Originally, his signal was over-equalized. He shut off the transmitter equalization, and he got 2 times more eye margin. Look at it right there. So I asked him, well, that's amazing. Good for you. How'd you do that? And he gave a great answer. He said, well, I went and found the transmitter's EQ register like you told me to, and I did it. So there's a little pro tip. I'll explain kind of why that works in a second. But if you think I'm inferring that you need to get into the world of EQ, that's exactly what I'm saying. I'm encouraging you to educate yourself on the different aspects of equalization. There's a bunch of terminology there. I'm pointing to the chapter in my book where I give a primer on equalization and explain what these different terms mean. Really, for today's signal integrity, these terms are just as important as the things you're used to thinking of, like stack-ups, return currents, transmission lines, these kinds of things. It's imperative that you start learning and educate yourself on equalization and how it works. So the reason why you can simply turn off your transmit equalizer in many cases is because the equalization in your receiver has become extremely powerful. And so this can typically handle most of the signal integrity, signal recovery problem. And it's even doing a great job at optimizing itself. So what's not intuitive is many of the features that are in receivers now are completely redundant with what's in the transmitter. So it's better to use your transmitter to get the full amplitude and not burn amplitude on equalization. However, it may be helpful to use your transmitter's equalization for precursor, in other words, ISI or noise that occurs before the transmitted bit. Most receivers cannot do that. So one way you can figure out if you have precursor noise before the transmitted bit is to examine your channel's pulse response. If you look at the two different pulse responses I'm showing here in red and blue, you can see that before the transmitted bit, which occurs right here at UI0, you can see, oh yeah, I have ISI, I have voltage that is spreading into the precursor space here. Now the pulse response is your perhaps best secret into getting your channel designed correctly, both passively and actively. It is the channel's fingerprint, and that's the term I usually use when I write about it, both in the book and in this online article over here. So I encourage you to use those resources, because even mathematically, the channel's pulse response tells you exactly what's going on. So in this scenario, I'm showing, again, two different pulse responses. I have the blue one and I have the red one here. And both these types of channels can close the eyes in different ways, but it's pretty easy to see that the loss-bound channel in blue doesn't have a lot of amplitude on the transmitted bit, and then has this fairly linear decay right here. That produces an eye where the eye is completely closed, although you still see some low frequency voltage. So that type of channel you're going to equalize in using certain parts of your transmitter-receiver equalization to solve that problem. Now, the discontinuity channel you see has lots of amplitude. It's off the chart here. And then it's very jittery. It looks noisy. It bounces around. And this type of channel causes a eye that is also closed here, but it's almost there. There's just so much disturbance in both voltage and in time that its eye is also completely closed. So the key takeaway here is your pulse response shows you what type of channel you have, be it loss bound or discontinuity constrained, and how to EQ it, because even though I see noise, ISI, all the way out to 60 UI, these are very messy, but I can look at the pulse response and even mathematically determine how I'm going to equalize this channel. So this is a very deep, but a great topic. And so in my hands-on class, with the click of a mouse, you simulate trillions of bits, and you learn how to tune the EQ dials, what does what gets in the way, what helps the problem on what type of channel. So I encourage you to join me in that class, because this is one of the most important things. Again, the #1 cause of failure. So let's learn how to get this right. So this is why my class takes a deep dive. There's a couple really interesting labs in the class. I hope you can join me there to try that out. Take it on a test drive. The other thing I think that is key here is that today's EQ does a much better job of handling loss than it does handling discontinuities. So that's why I say the best way to handle your discontinuities is simply to design your discontinuities out, or at least minimize them. Because in practice, a nice, smooth connection really doesn't exist. It's sort of unfair for me to draw it that way. It looks very clean, looks very simple, but it really, to an electron trying to move through there, or a rising or falling edge, it sees all these speed bumps and dips along the way. And those occur maybe at your breakout routes, your AC caps, connectors, vias, etc. All the different cables and things that make up your passive connection from the TX to the RX. So when we go through these different features, passive features, they may change impedance on you. So if you have an impedance change, you get a signal reflection, and now you have what's called ISI, and your signal integrity is damaged. So a discontinuity is every place in your passive connection where your impedance changes. So what do you do about that? Believe it or not, now this is perhaps the funnest slide in this webinar. Here I'm giving you 8 solutions, and I'm not going to go into great detail, because if you go to my author page at Signal Integrity Journal, as I'm showing over here, you can go into any one of these solutions and you can learn about it and solve the problem, as stated here as a solution. Believe it or not, some things we worry about, we don't need to worry about. They're too small. They're just not simply seen in my data rate. So I see this all the time. People field solving really tiny structures that are irrelevant at the data rate of interest. So that doesn't sound like good engineering, but still, it is good engineering to know what matters when. The second thing you can do is simply remove it. It's better to get rid of a discontinuity before it even exists. I look at designs sometimes and they want to put a connector here, and I say, no, that's going to be a problem. Let's just use a flex PCB so we can change the plane. And so sometimes that's the best solution. Just don't even let the discontinuity happen. Of course, this is perhaps the most talked about solution is to match the impedance. But again, as I already said, you can equalize it. You can even distance and dampen it. So I'm going to refer you to those articles. And I want to spend a little bit of time on which discontinuities we can ignore, because this I've written a good deal about. And the answer is understanding the relevant feature size, or the RFS. So here I'm showing how the RFS changes in size as we move to higher and higher data rates. So at these kind of data rates, we better get our trace impedances right. Around here, our via impedance becomes important. Now we're into connector pads. If you think about where we are now in these 3264 gigabit per second interfaces, 20 mils, that's your BGA pad. Just about everything now is relevant at these higher data rates. So I'm not going to go through everything on this cheat sheet, but I want you to have a copy of it. Of course, it's printed in my book. This is talking about many other things, but that is perhaps the number one thing I do when I'm seeing a new interface and I've got to figure out what to do. I orient myself in time and space and say, oh, okay, wow, I just jumped back to 8 gigabits per second. So now I need to be concerned about these kind of structures and not those. And you can think of those, I find it convenient to think of those in terms of their size. Now, in my opinion, the best way to understand your discontinuities is to look at a TDR plot. And I'm showing an example of one here. TDR stands for time domain reflectometry. And the reason it's so good and so helpful is it not only shows you the magnitude of your different discontinuities, but it shows you in time where they occur. And so if you know what system you're measuring, you can generally figure out how to translate the time to a distance. So for example, I'm showing you a backplane TDR, and because I know the system, I know, okay, here's my transmit card. I've got some breakout trace. I have a fairly long differential route to a connector complex here, which has some discontinuities. However, those aren't as big as the big backplane vias. This is from the press fit days where the drills had to be so large. They created very significant discontinuities here at these backplane vias. So you have some holes that are drilled bigger than we want on the backplane, and often on the card too. And then we have some routes, a differential route to another backplane via over to the receiver card, which has its own set of discontinuities. It's important to understand that you can get TDR data from a variety of different places. You can measure it using a TDR, or you can measure it using a VNA and then transforming your frequency domain data into the time domain. This is a very normal transformation from a set of S parameters to go either way, from TDR to frequency or from frequency to time in the TDR. Also understand that simulators create this data as well. Now, before I leave the subject of discontinuities, here's perhaps the most famous of all discontinuities, the stub. At this point in history, we've become very good at backdrilling vias to remove stubs. This was causing failures at the data rates shown. At the newer data rates we're bringing into production now, into volume, here's a stub. Those red boxes, those represent stubs. This is showing you what's bad. This is showing you how to fix it right here. So don't via in pad up to this side of your connector pad, because your solder pad, because you will create a big long via. So this, I've been watching a number of failures occurring because of this practice, which needs to be fixed by doing this. In the future, we have another stub that I really don't hope doesn't happen. And I'm talking with the PCIe Gen 7 folks who are still wanting to do it edge finger, but to do that without stubs, that has to be done like this, if you think about it. So let's move into crosstalk now. Crosstalk is something you probably hear a lot about and think a lot about. But what I'm going to raise to you now is crosstalk not where you expect it. It's crosstalk not in the same layer, but crosstalk between layers. Now, in a world where we shield all our layers, how and why does that happen? Well, think about it for a second. You make a good number of cutouts in your shield layers or your plane layers. And in fact, you're doing that to fix the previous problem, which was discontinuities. So we have to be careful not to fix one problem and create another. So here's an example. These are capacitor cutouts under a capacitor, trying to make the impedance of that capacitor and its associated solder pads match the interconnect. But look at what's going on here. I've got a very hot TX signal coming in, hitting the capacitor, and then coupling back onto an RX signal there in blue. So if you sum the coupled length, you come up with 120 mils. Now that's actually enough to cause a failure in your system. So you need to make sure you always use route keepouts under your voids. You keep your shield layers in place, and in the same layer, keep your gaps up around 25 to 30 mils. The best solution I've found for this problem is to visually check your layers. But again, if the route keepouts are there, then this won't happen. So why is it that 120 millivolts can close an eye? Here's a very interesting chart that is showing eye height collapsing in these different colors based on how much couple length you have. So the colors represent different gap distances. So that's the gap shown here, layer to layer. Now in that previous example, that was about a 6 mil gap. That's a pretty normal, you know, with 3 mil cores and dielectrics, that's a pretty normal distance for signals to couple through a missing plane layer. And look at what's happening. Only 1 mil of coupling gives you 1 millivolts. If you have eyes that are, maybe have 20, 30 millivolts of margin, 30 millivolts of coupling are going to close your eye. In the example I showed you, we had 120 mils of coupling, so we're right here on the chart. So we've reduced an eye that was maybe 140 millivolts down to 20 millivolts, and we've got failure. So these are the new kinds of problems. It's not that they can't be solved, but you need to be looking in the right place. You need to be thinking about your system in a new way and solving problems perhaps in a new way, as I've suggested previously. So this is what I refer to as the second generation, or Gen 2 of signal integrity. So before I close, let's talk about that for just a minute. Serial links for about 25 years now have really been driving and defining what high-speed connections are and how they work. They're completely changing how we do signal integrity. And so, as a practitioner in this field, from the very beginning, I've had to adjust my own thinking. And I've had to start explaining, well, what we're doing now is Gen 2 SI. So how did we get here? Well, as I said, about 25 years ago, we started doing serial links. And this technology has legs. I mean, we're way more than 50 times faster at this point. So the driver for this was something Intel stated way back in 2002, because they said, you know what? To go faster now, it's cheaper to use all our extra transistors than to put down new PCB traces. Well, that's interesting. I thought signal integrity is on the PCB. Well, this is ushering in a new era where the level of silicon integration is giving us a whole new kind of signal integrity. Now, in terms of the way I've showed it to you in this webinar, you remember the blue signal, right? Passive interconnect, so on and so forth. Well, silicon integration has enabled us to recover the logic level, and that was the red signal, right? So it's kind of a fun and funny coincidence that signal integrity and silicon integration are both SIs. So you put those two together, and for those of you who are visual, here's a picture of what Gen 2 SI is all about. If you're more technical, here's the contrast, okay? We started with, inventing this whole world of signal integrity. Now, fortunately, it's become just basic practices, a subset of things you have to understand compared to all the things that we used to worry about. And that's been enabled by the dynamics of the industry, right? We have ICs 1 million times more dense now. It's taken us to data rates that are 5,000 times faster. Of course, things have changed, but in practice, SI has become a bit simpler. So this is what I teach now, and I hope you'll join me. This is Gen 2 SI. These are some of the places where it's going to happen. I'm doing some private corporate classes as well. I'm successfully taking not just signal integrity engineers, but also hardware EEs, and showing you quickly what matters, how to solve it, how to use the things you're doing in your lab, bring up maybe to just work smarter and to achieve signal integrity. I hope you'll join me there. And please reach out to me and enjoy my book, perhaps, or if I can help you with signal integrity coaching, training, or consulting, visit me at sciguys.com. So I want to thank you for your attention as we've learned how to make your serial links work right and achieve signal integrity in practice. If I can help you at all in any way, do not hesitate to contact me.